Hi, my name is Claudia Avalos. I am an assistant professor at New York University. So my primary interest is in defects in solids, as well as optically induced hyperpolarization methodology. I'm working on a variety of different things right now. So like I said, we are interested in looking at defects in solids. So we're looking at defects in perovskite materials. We collaborate a lot with groups that are interested in developing new solar cell technologies. And so in this case, we're taking some of their samples, analyzing and characterizing them with NMR, and trying to understand what are the properties in those materials that lead to the function, right? So lead to the desired voltages that they read out in their devices. So that's part of the research we're doing. We're also working on developing new optically induced hyperpolarization methods at low magnetic fields and also high magnetic fields. So we're looking at small molecules, how they can be applied for optically induced DNP. So those are kind of the two areas of research that we're working on, and we're also doing some theoretical calculations as well in the lab that complement both of these types of research. So in our lab, we use both NMR and EPR. So in the case of NMR, like I said, NMR is very useful for looking at systems that contain defects or that are slightly amorphous. And in this case, it allows us to identify incorporation of defects into some of these perovskite materials. It also allows us to identify distortions in some of these lattices. So we're also looking at ferroelectric materials. And so as we modify, let's say, the surface of some of these materials or prepare them differently, we can look at changes in some of the NMR parameters as a guide to how this is changing the local structure. So that would be the case of NMR. In the case of EPR, and what we're interested in is how light is then changing the spin polarization of our system. And so for EPR, we use transient EPR methods where we shine a laser, and then we subsequently see how whether the signal is enhanced in the EPR signal or not. And so what does this tell us? This tells us how the one part of the molecule is coupled to the other. So the part, let's say, it's all connected, but in principle, you can think about it as you're shining the light. The chromophore part of the molecule is absorbing that, and then you have some coupling between that part and your radical that's tethered in your chromophore radical system. And then we can understand a bit about how these systems are coupled to one another. We are using EPR also to characterize some defects that we see in solar cell materials. So we can try to see, whether there are defects or there are paramagnetic centers in some of these materials. It's not necessarily the main way that we're using EPR, but in principle, you could use it for that. In terms of other things that we use EPR for, but primarily what we use it for is to look at these chromophore radical systems, right? And to understand the local structure or hyperfine coupling that exist in some of these radicals that we're looking at. And these radicals then would have potential use in DNP, for example, dynamic nuclear polarization, which then has a bunch of uses in material science and things along those lines. Yeah, so our aim, like I said, we have the NMR research that we're doing. We're also working on the EPR side as well. So with regards to the NMR, if we can understand how modifying a material can improve its function, the clear benefits to society are that, okay, we now understand how to maybe improve this material to then improve the function, right? So for the case of solar cell devices, right now we understand if we dope it with this material, we get a better optical response, for example, more efficiency of this device. So that would be one example in terms of the NMR. For the EPR, for these chromophore radical systems, our interest is in developing new polarization agents that can be used for hyperpolarization NMR without microwaves. This would then facilitate the use of DNP methods for material science at a lower cost, let's say. So this would be a little bit more method development, understanding the spin physics of small molecules and how they could be applied for dynamic nuclear polarization techniques. We'd like to sort of continue to develop a lot of these techniques and expand what we can do in the lab by building new adapters to some of our existing probes or our existing EPR systems, implementing more complicated optical schemes to then sort of expand the kind of experiments that we can do. But ultimately, we want to develop new methods and understand a little bit more about how different types of defects affect the function of different types of solar cell materials or photoactive materials.